All right, today we're pulling back the curtain on a device you definitely use every single day, but probably never think about: the network switch. We're going to break down the fundamental magic that brings a little bit of order to the absolute chaos of our digital world. I mean, it's so easy to take for granted, isn't it? You click a link and poof, a web page appears. But behind the scenes, there is a constant battle going on against digital chaos, just a storm of data packets flying everywhere. And the quiet, unsung hero of that whole story is the network switch. Okay, so let's dive right in. To really get why switches are so brilliant, we have to go back and understand the messy, messy problem they were designed to solve. And that story, well, it starts with their much simpler and frankly, much dumber predecessor, the network hub. So, I want you to imagine two people trying to shout into the same skinny pipe at the exact same moment. You wouldn't be able to understand a word either of them said, right? That is basically a data collision on a network. The electrical signals literally smash into each other, corrupting the information and making it completely useless. To deal with these constant collisions on those old hub-based networks, engineers came up with a set of, well, politeness rules for all the devices sharing the same wire. It's a protocol with a real mouthful of a name: Carrier Sense Multiple Access with Collision Detection, or, CSMA/CD for short. And yeah, this slide just lays out the whole chaotic process perfectly. A computer would first listen to the line to see if it was clear. If it heard silence, it would start sending. But of course, if another device started sending at the same time, bam, a collision. Both devices would then scream out a jam signal to let everyone know there was a crash. Then they'd each wait a random amount of time and just try the whole thing over again. It was all about listening, shouting, and then just hoping for the best. As you can probably imagine, this system was just incredibly inefficient. It didn't scale at all. I mean, the more devices you added, the more collisions you got, and the whole network just slowed to a crawl. This massive traffic jam is what led to the invention of a much, much smarter device: the network switch. And this right here, this slide just illustrates the core difference perfectly. A hub is like a megaphone. When it gets some data, it just shouts it out to every single device plugged into it. A switch, on the other hand, is like an intelligent mail carrier. It actually looks at the destination address on the packet and delivers the data only to the one person it's supposed to go to, creating a private, one-to-one conversation. So how does the switch actually pull this off? How does it manage to go from being a loud megaphone to a super efficient mail carrier? Well, it's all about intelligently dividing the network up into separate, smaller pieces. The key concept here is something called a collision domain. You can just think of it as a zone where data crashes are able to happen. With an old hub, the entire network, every single device, was one giant collision domain. Any two devices talking could cause a crash for everybody else. But a switch completely changes the game by creating a tiny, separate collision domain for every single one of its ports. Okay, so this brings us to a really common question, one that honestly trips a lot of people up. Since switches are designed to solve the collision problem, you might think they reduce the number of collision domains. What do you think? True or false? So get this, the answer is actually false. It's kind of counterintuitive. Switches don't reduce collision domains, they dramatically increase them. They create a tiny, isolated domain for each and every connected device. It's like turning a chaotic, one-lane road into a massive expressway with a private, dedicated lane for every single car. And this is exactly why more is better in this case. With each device chilling in its own little domain, collisions are pretty much eliminated. And this allows for what's called full duplex communication, which is just a fancy way of saying a device can send and receive data at the exact same time, because its lane is totally clear. No more waiting and no more crashes. Now, it's really important to know that while a switch is a super smart traffic cop for all those individual conversations, it does have a limit. If it gets a broadcast message, an all-points bulletin that's meant for everyone on the network, it will still forward that message out to every single device. Stopping those big network-wide shouts, that's actually the job of a different device called a router. Okay, so we know a switch knows where to send data, but now it's got a decision to make. How should it send it? And right here, it faces a classic trade-off. Do you want speed or do you want accuracy? So the first option is called cut-through switching. Think of a nightclub bouncer who just glances to see that you have an ID in your hand. He doesn't care if the picture matches, he's just trying to get you through the door fast. That's cut-through. The switch reads just enough of the data to see the destination, and it immediately forwards it. It is incredibly fast, but it might be forwarding corrupted junk. Now, the second option is the complete opposite, store and forward. Picture a different bouncer. This one takes your ID, checks the picture against your face, maybe runs a background check, and writes down your name and address before finally letting you in. This is store and forward. The switch receives the entire data packet, stores it for a moment, runs a full error check on it, and only then does it forward it. It's way slower, but it guarantees that no bad data is getting through. And the final method is this really smart compromise called fragment-free. So now our bouncer, he checks that you have an ID and he makes sure the picture actually matches your face, but he doesn't write down all your details. The switch does something similar. It reads the first 64 bytes of the data packet, because that's where most of the errors from collisions tend to happen. If that first part looks clean, it forwards the rest, giving you a nice balance between speed and reliability. So this table really just wraps up the bouncer's dilemma perfectly. You can see how cut-through gives you the lowest latency, or delay, but with zero error checking. On the other end of the spectrum, you have store and forward, which has the highest latency but does a full check. And right there in the middle, you have fragment-free, offering a really practical balance of both. All right, finally, there's one last real-world wrinkle we need to talk about. You have a computer, and you have a switch. How do these two devices agree on which rules to use in the first place? Like, what speed are we going to use, and are we talking one way at a time or both? Well, they use this really clever feature called auto-negotiation. The moment you plug a cable in, the two devices perform this quick little digital handshake. They basically just tell each other what they're capable of doing, and then they agree to use the fastest, most efficient settings that they both support. Pretty smart. But while that sounds great in theory, this quote from Cisco kind of highlights a common real-world problem. Sometimes this automatic process can fail, maybe because of bugs or different manufacturers implementing this standard just a little bit differently. And that can lead to a really frustrating mismatch in the settings. And this is why it really matters. A failed handshake leads to a ton of errors and a painfully slow connection. So, in supercritical environments like data centers, network engineers often won't even risk it. They'll just manually disable auto-negotiation and hard-code the settings on both ends to absolutely guarantee a stable, reliable link. So, what's the bottom line here? Network switches are basically the intelligent traffic cops that make our modern internet even possible. They solved the absolute chaos of data collisions by giving every single device its own private lane. And they are constantly balancing that need for raw speed against the need for accuracy. Without them, we'd all still be stuck in one massive digital traffic jam. So the next time you click a link and a page just instantly appears, maybe you'll think about the silent hero making that happen. Understanding how a switch turns what was a digital shouting match into a whole series of quiet, private conversations. Well, it's a little peek into the vast, invisible architecture that powers all of our connected lives.